All right, so we have same plane, diving, then climbing. Same plane, so it has the same weight. So let's go ahead and put the weight vector in. The weight vector we know is going to point straight down. In each case, it's the same. Weight is equal to, what is it? Yeah, it is mg, but what's the value? Huh. 5.9 times 10 to the fourth newtons. Okay, that's the same in each case. So we'll just make it the same. All right. Then we have the lift, which is the same in each case. The lift is blue. Blue lift. All right. Now, what's important about the lift already? You're already thinking, oh, Mr. Combs, you don't even need to put the lift on there. Why? Think about the displacement vector. Yes, it's perpendicular. It's perpendicular to the displacement. It's going to do no work. So, did they even give a value for the lift? Well, I heard a yes and a no. So is there a value for the lift?
The lift force L acts perpendicular to the displacement x, which is the same as
1.7 times 10 to the third, that's the lift? But we don't even care. Oh, that's the meters of displacement. Okay. So you can see that they didn't even give you the lift. Did anybody, when they were working this problem, say, wait, we don't know what the value of the lift is? Did you say it? You probably said it just like that, too. All right, so here, since these are perpendicular, we know that the work done by the lift in each case is 0. We don't even need to consider it in terms of the total amount of work done on the plane in the dive versus the total amount of work done in the climb, okay? Since it's perpendicular, work done by lift is equal to 0 in each case. Is everybody okay with that? Cosine of 90, 0. Also, qualitatively thinking about it, it has no component that's either parallel or anti-parallel to the displacement. All right, in each case, we have a displacement vector of, that's the one that I need from you. Displacement is equal to, it's 1.7 times 10 to the third meters, right? 1.7 kilometers. All right, so I'll just put it over here. They're supposed to be the same size, but we're not going to worry about if they're exact or not. So here, displacement is equal to 1.7 times 10 to the third meters. Okay? So, I'm missing a vector. There's one more vector. I know what it is. Do you?
Thrust.
Thrust. Okay, thrust is the same in each case, and notice that it's parallel, exactly parallel to the displacement. So when we do the cosine of that, it's going to be 1. So we can just say F times D for that, right? Instead of worrying about FT cosine theta, we can go, oh, theta is 0, so cosine theta is 1, we'll just leave it out. Not leave it out, we've already accounted for it. But here, thrust has a value. What's the thrust?
It has the same magnitude during the time. It doesn't say, I don't think.
We don't have a value for it? Okay, I guess the way they ask the question, then we don't need an absolute amount, we're just looking for differences, right? There's two parts. What are part A and part B? Oh, okay, so in other words, the first one's just qualitative. All right, so now looking at this, since the work done by the thrust in each case is going to be the same, the work done by the lift in each case is going to be the same, 0. So the only difference between A and B is going to be the work done by what vector? It's not very obvious. Yes, and in fact, it's gravity. In fact, it's just one component of gravity, isn't it? Right? It's just going to be the part, in this case here, that's parallel, that right there, and in this case, it's anti-parallel. So in which case is more work going to be done by on the plane in total? In the dive, sure. Think about it. Work is going to be equal to change in kinetic energy. In which case would you expect the plane to speed up, or at least to speed up more, or slow down less?
We were confused at first, but then we thought, okay, like it's all like combined work in the same direction. It's not the way we think about it. Like what we think about that it takes more work to go up because it's like going against gravity.
To have the same change in velocity, you would have to do more work going up, right? Or let's say this. Let's put it this way: this would have to do more work. The thrust vector would have to do more more work to account for the negative work done by
Yeah.
that component of the gravitational force, right? So that's in order to be at work at a constant, go move at a constant velocity, that would be true. But if we know that this is constant, the two purple vectors are constant, then in one case we're going to have more work than the other, okay? So the difference between them, since we've already answered A, conceptually we can see that more work is done in this situation right here in the dive, right? Because we have the positive component of gravity. All right, so how are we going to find out the difference in the work done? It's pretty easy. The only difference is the positive work done over here versus the negative work done here. Okay? So work, the difference in the work, the change in work, or the difference in work is going to be equal to, we'll pick one. We'll say this one is the work done by gravity, right? I'm going to say use W for weight because we gave that as the weight vector, right? So the work done by W, or weight, in the dive minus the work done by the weight in the climb. Okay? So that's going to be the only difference, because we could say that the total work done is all of the work done in this minus all of the work done in this, but we'd just be subtracting this times distance from this times distance. That would be the same. Subtracting 0 from 0, that would be the same. So these are really all that's left. Is everybody okay with that? Okay. So moving on, the work done during the dive is going to be the force, that the component of the force that's parallel. Let's do it this way. We'll do FD cosine theta. FD, the force of thrust, or the force of the weight, is the same, right? Force of the weight is the same in each case. The only thing that changes is cosine theta, isn't it? So watch what we're going to do. FD cosine theta is going to be weight times the displacement times the cosine of what angle right here? Now be careful. What is the angle that we're going to be using? The angle between the force and the displacement. The angle between the force and the well, here's the force that we're talking about, is gravity right here. All right. So that if it's diving down at 15 degrees, is that correct? 15 degrees below the horizon. Well, actually, we were given this angle right here as 75, right? So that's the angle between them. What's that? Angle of 75 degrees. It's the angle between them. We don't have to worry about if it's pointed down or up or anything like that. Minus the weight, because it's the same vector, right? Times the same displacement, times the cosine of what angle in this case? What's this angle right here? It's given as 115 degrees, correct? No, we don't say 25. We still have to say, the entire angle between the force and the displacement, right? Remember, we don't care anything about the frame of reference or an axis. We don't care, because because work and energy are not directional. They're scalars. So we just find the angle between them, which was given as 115 degrees. All right? So cosine of 115 degrees. And what do we know about the cosine of 115 degrees? It's going to be negative, right? Here's our cosine curve right here. Looks like this. And this is 90 right here. And this is negative 90 or 270, right? So anywhere in between here, it's going to be negative. So we're somewhere here. It's going to be a negative number. So now when we're finding the difference, we're going to be taking this minus a negative number. So we're going to be getting a positive number. And we'll see that the numerical answer we get will be consistent with the conceptual or qualitative answer we got when we said that it's going to be, the more work is being done on the plane when it's in the dive. All right, so now we can just pull WD out of each case. So WD, that's the weight times the distance, times the cosine of 75 degrees. Get out your calculators and start doing this while I'm writing, please. Minus the cosine of 115 degrees. So that's going to be weight, which was given to us as 5.9 times 10 to the 4th newtons, times the displacement, 1.7 times 10 to the 3rd meters, times the difference between cosine of 75 and the cosine of 115. What's cosine 75? We'll just do the whole thing in there. That's just going to give us a positive number.
0.68. But that's the total.
That's the total? 0.68, and it is dimensionless.
I get a negative answer.
Okay? You won't get a negative answer
Oh,
because we have a positive minus a negative. So we're going to get a positive answer that's bigger than the positive number, right? So now when you put all this together, and what's this? This is the difference in work. Okay? We're not, remember, work is change in potential, or I'm sorry, change in kinetic energy. So don't confuse W is equal to delta K with what delta W is, and that's the difference between two changes in energy. So it gets a little wiggy here, okay?
6.83 times 10 to the 7th.
6 point what? 83 times 10 to the 7th, you said? All right, so let's look at our units here. We have Newton meters. This is dimensionless. So Newton meter is a what? A joule. Yes, it is. So the difference in the work between the dive and the climb is 6.83 times 10 to the 7th joules, or 68 million joules, right? The amount of energy necessary to lift 68 million quarter-pounders. Dang. That is all.
That is